Hey everyone, so now I'm going to walk through the Welch's t-test lab. It seems pretty straightforward. I think it just wants us to write out a function to calculate the Welch's t value or t-test. That's the formula that we had right there. Hang on, I'm just gonna, okay. So I have my outline on the right, which isn't particularly helpful at the moment, but anyways, okay. Write a function for calculating Welch's t statistic using two samples A and B to help. Two potential samples are defined below. Okay, it's just going to create the control sample, which is a normal, it's pulled from a normal distribution. The mean is 10, the scale standard deviation is 1, and the size is 8. So there's 8 individual numbers in this sample, and in the treatment, the mean is 10.5, the scale standard deviation is 1.2, and then the size is 12. As you may have read in the README, the Welch's t-test is used where we are unable to meet the assumptions that we need in order to use a student's t-test, i.e. that the two populations that we're conducting t-tests on have they have the same variance and they have the same size. And if we can't meet those two criteria, then we have to use the Welch's t-test instead, which is more accurate in that situation. So we're going to do those. Just going to print out those and see what's in there. Okay, it just generated these random arrays for us. Now let's write our function. Okay, so let's take a look at the Welch's t-test formula. So t is equal to x hat minus x2 hat. So these are the means of the two samples. So what I'm going to do is I'm just going to do x1 hat is equal to, if it's an array, I can just do a dot mean, right? And then let's do x2 hat, and that's going to be b dot mean. What's the next thing? Okay, it's s1 squared, where x hat, si, and ni are the sample mean, the sample variance. So let's do s1 squared, which is equal to a dot how do you get the variance? Hang on, let's see. I already did join it. Leave me alone. Okay, numpy array variance and numpy.var. Okay. Compute the variance along a specified axis, so you have to pass it in there. Okay. There's no method for it. You can't pass it on the array itself. So let's do np.var and pass in a. That should give us the variance of a. Yes, I know. And we're going to raise that by 2. So now let's do the second sample's variance squared, which is going to be np.var b. Again, we're going to do the 2. So that takes care of our denominator. Let's do n1 is equal to the length of A, and 2 is equal to the length of B. Yeah, because it's right where ni is the sample mean and the sample size, so we just do length of the array that we passed in. So that should give us all the elements that we need. And now we can just calculate the t, which is going to be equal to, let's do the first bracket. So it's going to be x1 hat minus x2 hat. And we want to divide that by, and then we want, what do we want? np dot square root, yeah, of, I want to do those in brackets as well. I like using brackets. Like, it's just easier. Just put stuff in brackets just to guarantee that they'll go in that sequence as opposed to trying to remember all the PEMDAS rules. And so the first one, we want s1 squared over n1. So let's do s1 squared over n1. And we want to add to this s2 squared over n2. That should do it. Yeah. Okay, let's see if our brackets are all good. Yep, that term is in there, that term is in there, and then I think there's an extra bracket. No, because then that does the square root, and then, yes, it is extra, because we don't need that, because that's a denominator. So an NP square root, that's going to cover all of this. Divide. I think that should do it, and then just return t. Let's see if that works. What do you mean invalid syntax? I know what this is. This is going to be some nonsense. Oh, that's because I guess I did need that bracket after all. Okay. NumPy has a typo. I swear this thing is not good for me. Okay. What now? Oh, it's this stupid autocomplete thing. I really got to shut it off. Oh. Why didn't it give me the right one? That's nonsense. What did I do? Control, treatment. Did I do the thing wrong? Wait, it said something about absolutes, right? Important when the designing it is appropriate to take the absolute value of the t-value. Well, I mean, still, that still shouldn't be different though, right? What if we switch it around? Oh, because I didn't square. No, but I squared it up here, so that term is squared. Maybe I should switch them around. Maybe I'll do like x2 hat first and then x1 hat. See what that does. No. Oh, it's still giving me the same thing. What the hell? Why? Is it the wrong one? What am I doing wrong here? I don't know. X1, did I square rooted it, divided it by n1 and n2, and I squared up here. Sample variance, sample mean. What am I doing wrong? I don't even know. Should I skip and keep moving? Ugh, for sample I. Okay, I'm gonna check it again. What am I doing wrong? It looks fine. I don't know what the problem is. I don't know what the problem is. I don't know. You know what? I might just skip to the solution and see what's going on. Or maybe their thing is wrong. I don't know. Let's just keep moving and we'll come back to it. Once you have the t-score, you need to calculate the degrees of freedom to determine the appropriate t-distribution and convert the score into a p-value. Okay, so the effective degrees of freedom can be calculated using, okay. Okay. The variance, or the V is the degrees of freedom for sample I, equivalent to n minus, oh, I see, okay. So let's do that now. Since we already did S1 and S2 squared up here, I kind of want to copy these down. But since it doesn't work up there, I'm scared that it won't work down there either. But I'm just going to do it anyways. Actually, I could also do N. I'm just going to, okay. And then we have N squared into V. Oh, we also need to do the V's. Well, let's do the S Q, like raised to the power 4. S1 4 is equal to NP dot variance. Oh my God, maybe that's what I did. Hang on. No, I don't think that's gonna help, but maybe it's worth a shot. Maybe, who knows? It didn't do jack. So let's go down now. np dot var a raised to the power 4 s24 is equal to np dot var b power 4. V1 is going to be equal to n1 minus 1. V2 is equal to n2 minus 1. It takes care of that. And now let's just do our formula. So I'm going to split it up even further. The numerator is going to be, hang on, I'm going to copy this into my outline so that it's easier for me to refer to it. Variance, is that the variant? Whatever, I'll figure that out later. Oh wait, hang on, escape markdown, okay. Oh, I hate. All right, that's why I don't have to keep scrolling up. So the numerator is equal to S22 divided by N1 plus S2, no, S1, oh, no, wait, hang on, this is S1, this is S2, 2 divided by N2, that's our numerator. Our denominator should be S1, 4 over N1 raised to the power 2 and multiplied by V1, and we're going to put that in parentheses, and we're going to put that in parentheses as well. And I kind of want to split that out into a line as well, but I won't because I'm already going. So it's going to be S2, 4, divide this by same thing. It's going to be, but this time it will be N2 raised to the power 2. Multiply that in turn by V2. And again, I'm paranoid, so I'm going to put this in brackets. Hypervigilance never hurts until you waste too much time on it, but better safe than sorry, that's what I say. Okay, that looks good. I think that should work. And then, oh, and then of course, finally, V is going to be num over the num, return V, and let us run it. What in the hell? What am I doing wrong? Why is it an array? I don't want an array. I don't need an array. What did I do wrong here, guys? So that's a number. That should also be a number. N1, and that should also be a number. That should also be a number. Oh! No. No, that should also, that's, oh, okay. Oh my God. Do you see that? Did you see that? There was like one A. You hit one wrong key. Please work now. Yes! Sorry for my excessive enthusiasm. I can't help it. But I love it when that happens. When you catch a bug and you fix it and then it works. Woo! It's fun. You know, they say that that's why people like roller coasters or doing dangerous activities in general, because like when you come close to a like a dangerous situation but you get out of it safely, you get this endorphin rush because it's designed to sort of, you know, it's like your way of like reinforcing whatever it is you did to escape the danger. There's like a biological mechanism that's kind of like trying to like, you know, condition you to like, okay, next time you see a lion, you also run away, that kind of thing. Anyways, enough sidetracking. So it's again, it's like slightly off, and I'm convinced at this point that that has to do with like the random seed being incorrectly specified, because it seems really close to me. So I think that might be it. But anyways, let's delete that. Now calculate the Welch t-score and degrees of freedom from samples A and B using your functions. And from samples, okay, we can do that. So the t-score is, oh, you mean do the same thing that we already did? Okay, fine. But I'm gonna be lazy about it. That's you know how they say that necessity is the mother of invention? Well, guess who the daddy is? It's laziness, folks. Because when you're lazy, you find shortcuts to do things. I mean, the guy who invented the car was probably just like, dude, I don't want to walk to the store. We need the machine that'll do the walking for me. And, 100 years later, we're all driving around. So, okay. It's 2 o'clock in the morning, and I'm just having a fun all-nighter, guys. Please excuse my banter. 2.3129. It's the same values that we got above, but yeah, they're slightly different. Convert to a p-value. Great. Now that you have the t-score and the degrees of freedom, it's time to convert those values into a p-value for a one-sided t-test. Okay? Remember that the easiest way to do this is to use the CDF function associated with your particular t-distribution. Calculate the p-value. Okay, fair enough. I had that method somewhere that I saved. We're gonna go to, why is it not showing? Okay, central limit, hypothesis. I believe it was in t-tests. I usually put the code snippets up here. Well, they don't have those. Well, that's also, so we're gonna keep going. Stats.t.pdf, that's right. No, but it's t.cdf, right? Cumulative distributive. Well, is that it? To get values on the probability density function. Well, that's on the probability density function, which that would give us something else. That would give us the associated statistic for that t, whereas we're looking for the probability, which will come from a CDF. I'm just going to go out on a limb and assume that there is a stats dot, yeah, I'm just going to do stats dot t dot. Okay, it's the fact that that didn't come up is making me nervous, which means I probably have to import it. Import numpy. Okay, yeah, it didn't import, so let's do an import. And I'm going to do it in the cell above. Import. I forget how to import. Import, wait, scipy dot stats. Is that how it is? Okay, so now we're going to do stats dot t dot cdf. I'm straight up just gonna do t, the degrees of freedom will be df. I don't know what. Hang on. Forgive me, I don't know how to bring up that help. Okay. Yeah, I know. Okay. Stats dot t dot cdf. Stats is not defined. Oh, really? But because I didn't do as stats. Okay. CDF, blah, blah, blah. X is the array. arg1, don't care. Lock is the location, scale, cumulative distribution function evaluated at X. All right, but I don't know where the, okay, whatever. I'm just gonna do what I was doing before. T, DF. So I think that's probably lock and scale, right? Oh, default is 0 and 1. So I think I could leave that as default because we're doing probability, so it's already done that for us. Oh, 1 minus, because that's a CDF. Remember, that's telling us how many values are up to that T. So we do 1 minus, and maybe that's right. I don't know. I think it's, again, we're seeing that variation. I'm just going to assume that that's correct. Now, this is only 2.5% probability. I'm seeing 1.6. Maybe I'm doing it wrong. But anyways, you would see a t-score equal to or greater than what you saw from the data. Given that alpha was set at 5, this would constitute... This would constitute sufficient evidence to reject the null hypothesis. Well, okay, we're doing that. Building on this, you can also write a function that calculates the p-value for given samples with a two-sided t-test. By taking advantage of the symmetry of the t-distribution, calculate only one side, right? The two-tailed p-value is simply twice the one-tailed p-value because you want the probability. Okay? T, where t is less than absolute. Okay, greater than what? Where t hat is the t statistic. Okay. Would that define a summative function p val Welch a b two-sided equals false, which takes in two samples as well as an optional binary variable to allow you to toggle between. Okay. The default behavior should be set to one-sided. Okay. If the parameter is two, then okay. Okay. So, well, let's just first of all, let's copy what we did before. Oh, it's going to do all of it. Oh, okay. It's going to be our degrees of freedom. So, okay. So the t-value will be both. We're just going to use it twice. And then the v will also be the same. So let's see. So let's get the t-value is equal to. Okay, so twice the p-value. Right, because it's symmetric, so when we calculate the p at the end, we could just take off the other at the other tail. So I don't know what the hell that is saying. I'm just going to ignore that. So let's just get the t-value. The t-value is going to be, what's the name? Welch T-A-B. Okay. T-value is equal to Welch T-A-B. Then let's get the degrees of freedom, which is Welch D-F-A-B. Righty. Okay. DF is equal to, in fact, I'm just going to even take that out. Because then what I know that I can do is simply copy over. Okay, import SciPy, and then, all right, so we're just going to do this p-value. That's going to be our p-value. We're going to copy that. We're going to paste that in here. Okay, and actually just multiply that by 2, honestly. Stop freezing on me. 2 multiplied by that, and that should do it. And then we're just going to return p. And let's see what that does. Okay, that did not work out correctly. What did I do wrong? Did I forget to take the absolute value of something? That can't be right. Hang on, let's see what the p comes back as. It should be the same as what we got before. Okay, that is also not right. Oh, because two-sided is equal to false. Oh, because but even then, the p-value should have still come back. Hmm. And it's the same. Hmm. Hmm. Well, let's okay, hang on. DF, that's fine. Because did I forget to pass in? No, no. If two-sided p is equal to p multiplied by 2, right? But that still should, I don't know why that's doing that. Treatment control. Why? Why, oh, why? That makes no sense because it should have been the same. I kind of want to give up, guys, and just get the solution. What do you say? Oh, wait, you're not there, so you can't answer me. All right. T is equal to Welch, T of A and B, df is equal to Welch, df, A and B, P is equal to 1, minus stats. That's all fine. So then why is it doing that? It almost feels like I shouldn't be subtracting it from 1. Maybe. That didn't do anything. Hang on. Hang on. You know what? I should have listened to them. And they say, okay, let's return ABS freedom. Let's see what, I bet that'll do it. Okay. Didn't do anything. So, no, wait, I did it wrong. Appropriate take absolute of the t value. Okay. So let's just return ABST just to be safe. Okay. Okay. Fine. Oh yeah. Okay. There we go. That fixed it. Did you see that? You got to listen to them. You have to listen to, yeah, that's okay. Because it probably made a difference because when you were trying to, and then over here they say the same thing where t, something about t being absolute. Because if it's the negative t value, then you're going to like the, oh right, because if you take the t value and it comes back as a negative, then you're going to like the left side of the curve, instead of this tail, and then so that'll give you the problem. So just the regular p value will be that, and then if you do 1 minus, then it'll give you all of it. Okay, I see what I did wrong there. Let's see if the second one works. Two side. Oh, two-sided. Okay, never mind. Okay, let's do that. Two-sided is not defined. Should have just fixed that. Okay, 0.03. So that's kind of off. Screw it. Let's just look at the solution. Okay. So let's go down and let's compare. What did they do? Okay. And let me go back to mine. Okay. np random.seed82 control. Okay. So yeah, I don't know why they get a different, let's see what they're doing differently. So they do it, the numerator is a dot mean minus b dot mean. Same thing, kind of. And then they do degrees of freedom. The divisor uses n minus DDOF, where n represents the number of elements. By default, the DDOF is 0. Okay, so the denominator they're saying is np dot square root a dot variance, so it's the variance, okay, and the degrees, so they're passing in degrees of freedom to variance, and I don't know why. Is n minus DDOF. By default, the DDOF is 0. Divided by a dot size. Okay, so then for some reason they're also, am I unnecessarily squaring the variance? Maybe it's just a question of I forgot the symbols. S squared. Okay, so that's redundant for me. Okay, so variance brings me s squared. I don't need to then square it. That would be the standard. That would be the standard deviation, right? Variance is already squared. Like, okay, so like a regular s without being squared is standard deviation. S squared is already variance. So when I'm getting variance, so that's what I'm doing wrong. So let's fix that. Also there is an a dot var. I did it differently. So let's try their method. Let's do a dot var and then let's pass in DDOF is equal to 1. And I don't know why they do that, but you know, let's see if that will change our results. Invalid syntax. What do you mean invalid syntax? God, that made it even worse. What am I doing wrong now? Plus b var DDOF is equal to 1 over b size. I don't get it. What's the difference? I don't know what I did wrong. Okay. I feel like that should be a cube. I don't know why that's not a cube. And right, but I did take n1 minus 1, so that's correct. Okay. And then threw my p-values off and everything. All right, so this might be something to bring up at study group and see what I did and where I went wrong.